The solar system is 4.5 billion years old, or 4.567 to be a little bit more precise. But how do we know that? How could we possibly date the age of the sun, for example? Now, we can see star systems forming all over the galaxy right now in nebulae. We can see protoplanetary disks as planets form around their stars, but how could we have dated our own? We need to be able to study an object that formed exactly at the same time as the sun was. Thankfully, we have just that. So this is a meteorite, a chondrite to be precise. So it's one of those cosmic dust bunnies that just collected everything that was forming in the protoplanetary disk, the disk of gas and dust that formed the sun and the planets. Dust and gas were constantly falling onto the newborn sun. And that dust, as it fell in, evaporated. Now, ordinarily, that dust would just become part of the sun. But sometimes, the infant sun had a little stellar tantrum, or as we like to call them, an outburst, is the more technical term. And as these outbursts happen, that gas that was really rich with just freshly evaporated dust was blown off in streams. So the gas that was streaming off the baby sun began to cool. And the dust that had been evaporated began to cool down as well and recrystallize, recondensing, almost like molten sleet. So if you imagine, rain and icy kind of sleety stuff, it was like that, but of ceramic-like materials, so silicates and oxides coming out of this stream of gas. And that's what these are, these little white inclusions that you can see in this sample. These are called calcium aluminium rich inclusions, or as we call them, CAIs. And we know that they form at almost the exact same time as the sun itself. And we can see outbursts like this happening when we look at freshly born stars in other places in the galaxy. Among the elements condensing onto these little CAIs was uranium. Now, uranium is an element with no stable isotopes. That doesn't mean that they fall apart in seconds. It just means that they have half-lives, in fact, of billions of years. So they're not stable, but they can last a long time. And that allows us to measure their abundances, or not their abundances, but the abundances of their daughter isotopes in these objects and calculate their dates. So in this instance, what we're measuring are the stable isotopes that result from the decay of uranium, lead-204, lead-206, and lead-207. So by measuring the abundances of these elements in these objects, we can plot their relative abundances against each other and calculate an age from that.